Okay, so there's one equation that has been following me from high school. So that equation is known as y is equal to mx plus c, right? Y equals mx plus c. And this equation has also transformed modern AI. Yes, when I say this simple equation has transformed modern AI, I do mean it. So I first encountered it when I was in high school. It was just an equation of a line, right? I just thought of it as a linear operation between m and x, and then we're adding c, and we simply get y. But then when we started studying AI, we thought of this equation as a linear regression equation. So it was an equation of an algorithm, or rather a machine learning model, right? Then we realized, okay, so y can be thought of as a predicted variable, x can be thought of as an input to that predicted variable, input for that predicted variable, and m and c are nothing but the parameters of a line. So when we think about line as a line in itself as a model, then the parameters of a line become the parameters of a model, right? And then we realized, now that they have become the parameters of a model, and models are learnable, models are trainable, so this equation is also learnable. The parameters m and c are also learnable and trainable. But how? The parameters are learnable because this equation is differentiable. I can always take the derivative and find the gradients and find the right direction where I need to move such that my loss function is minimized and I get my best m and best c to get the best y, right? So now that y is a predicted variable, y, we started using y as a variable that has to be predicted between ranging from negative infinity to positive infinity. Then we learned about nothing but y hat. So y hat was being used as a predicted variable, whereas y was being used as a true label, right? So now this equation taught us that y is no more just a simple point on a graph, right? Then what is y? Y can be thought of as a predicted variable, and y is nothing but a vector. So when y extrapolates into a column vector, x is also thought of as a column vector. Now, if I am predicting the house prices based on the size of the house, so x can be thought of as the size of the house, where x is also a vector, and house prices can be thought of as y, right, where y is also a vector. Now I could certainly stack all of my data points based on this equation, right? Then I thought, if this equation along with the loss function known as mean squared error is forming nothing but linear regression, but x is only one dimensional, is it always the case that my equation or my data set will only have one data or one column or one set of features? No. Then we tried to extend this equation. So y is equal to mx plus c became y equals to m1 x1 plus m2 x2 plus m3 x3 and so on m dxd, where d is the dimension of x plus c, right? Now what are we thinking? We are just thinking that y is something to be predicted, x is a d-dimensional data set, and c is the bias. All m1 m2 m3 have been extrapolated from this equation, right? Now we suddenly named it as a multivariate regression, right? We're still doing regression, we're still building a model. The only difference is, previously the data point, the data set that we were using in y is equal to mx plus c was thought of as one dimensional data, or basically x was one dimensional. Here x has been stretched to d dimensions, right? What this really taught us that this equation is sufficient and is agnostic of number of dimensions in your data. If you are only predicting house prices based on the size of the house, this works. If you are predicting house prices based on the size of the house, the location of the house, the carpet area, the super area, and a lot more d features, this equation still works. So linear regression, multivariate regression, this equation also taught us the word linear. The highest degree of polynomial is 1. So we could think of linearity with respect to this equation, right? So now when linear regression was already very much comforting, because we had seen this equation, we could fit a line, we could think of the line as a model. Then one more inflection point came when we infused in non-linearity into this equation, right? By using what? By using an activation function. The first activation function I ever saw was the sigmoid activation function. So I suddenly realized, why was a data point on a graph? Then y became a predicted variable. Now y can also be modeled as a probability, right? Because if I apply an activation function on mx plus c, that activation function converts all the negative infinity to positive infinity and squishes it between 0 and 1. I can think of it as probabilities. Now it has given rise to another algorithm, which is nothing but logistic regression. Logistic regression, along with a different loss function, which is binary cross entropy loss, is helping me classify between two classes, right? Class 0 and class 1. And the same equation. Now the same equation, y is equal to mx plus c. It's just that the same mental model is being followed. M and c are still parameters. X can still be extrapolated to d dimensions. Y was ranging between negative infinity to positive infinity, but now that activation function is trying to project it between 0 and 1, squish it between 0 and 1, y has turned into probabilities, or y can be thought of or modeled as probabilities. And this was not enough. When I started seeing neural networks come into picture between the 2010 era, neural networks changed everything. They changed speech recognition, image recognition. So during that era, so 1990s to 2010, it was all the neural network phase. So when we first encountered neural networks, we first treated them as black box. Then I suddenly realized neural networks are also following the same equation. Some people call it W transpose X, some people call it WX plus B, some people call it MX plus C, but it's the same line equation. Now it has just become nested. In multivariate regression, we extrapolated the equation horizontally or breadthwise. Y is equal to m1x1 plus m2x2 plus m3x3 plus m4x4 plus mdxd plus c, right? Now we have depth. So now this equation has become nested. X is an input, but X is not an input always coming from the dataset. X can be thought of as an input coming from the previous layer, from the previous layer, and from the previous layer. So it is a cascaded input coming from the previous layer, and so on, right? So now this equation has depth. Since this equation was always differentiable, by adding depth, we did not destroy it. The parameters m and c are still learnable. Now m and c obviously will grow in a non-linear fashion. Previously, when x was d dimension, we had d order of d parameters. Now they will grow non-linearly. Why? Because the equation has become nested. But why is it still differentiable? Because calculus came into picture. Calculus said, I will help you differentiate it. Use my chain rule, right? So since I have chain rule, I will help you take the partial derivative of the loss function with respect to all of the parameters possible, right? And cumulatively, you can call it a gradient and then optimize the neural network, right? So this was the first time when I encountered neural networks, saw this equation, had a moment. Wherever this equation comes, if it gives me a certain comfort. When I encountered convolutional neural networks, I realized as soon as I understand the convolutional block, I still have the same equation, which is part of the feed-forward neural network or the linear layers, right? When I encounter transformers, I again realize the same things. So after I pass through the multi-headed attention block, I still have to face this equation. The equation is still helping us predict y. The equation is still helping us add non-linearity, using the activation functions just like we used to do before. So this equation has taken me from high school to modern AI, and I think it might not take me to AGI, but still it has taken me that far and helped me understand a lot of algorithms, or rather all the algorithms from this particular mental model. So wherever I see this equation of a line, which was a simple line, now it has become, now we have learned how to model, nonlinear curves and do more and more complex nonlinear regressions using neural networks. But this simple line equation thought of in different algorithms and in different paradigms has changed my perspective to look at all the algorithms, and has also simplified all the algorithms in general. Thank you. I hope this was useful. Cheers. I'll see you in the next video.